Welcome back to Linear Circuits. This is Dr. Ferry. This lesson is on phasors. Our goal in this module is going to be able to look at a problem like this, where we've got a fairly complicated circuit with reactive elements in it, and we've got a sinusoidal input. And our goal is to try to find the output to that circuit. Now, we could use differential equations and solve differential equations for that, but it's really messy that way. So our objective here is to find an easier way of solving circuit problems with sinusoidal inputs. We're going to start out by introducing phasors to represent sinusoids. Now, the methods that we're going to go through in this module are based on a sound mathematical foundation, but it's very involved to be able to go through that mathematical foundation as to why this method is going to work. So we're just going to introduce the method and show how to use it in actual applications without going through the rigorous mathematical foundations to show you that it really does work. We're going to be building on some things that you probably had many years ago, and that is complex numbers. Starting out with, we're going to define the imaginary number as the square root of -1. Now, you've probably seen it as I before. I is equal to the square root of -1. Well, in electrical engineering, we use I for a different reason. We use it for current. So we use J to represent that imaginary number. We also will be looking at complex numbers, where A is the real part and B is the imaginary part. Now, the other thing we have to remind you about is trigonometry. So if I've got a triangle like this, then the opposite side is sine and the adjacent side is cosine. And that's with a hypotenuse of 1. So if I had a different hypotenuse, then I just scale it through. Let me define phasors. My sine wave is given in this form right there. And I'm going to define the phasor in polar notation as being this, where V is simply the amplitude and theta is the angle. And I show the phasor, I indicate it's a phasor by showing it as a bolded term. Now, it is a complex number, and I'm going to represent it, I'm going to draw it here as the imaginary versus the real part, as a vector, with an magnitude of the vector being V and the angle here, from here, being theta. Now, this is polar notation, and I can convert it to rectangular notation, where this is the real component of it, that's A, and B is the imaginary component. I can convert between rectangular and polar notation by looking at this as a triangle, with a side, the opposite side being B and the adjacent side being A. So I go back to my trig identities and trig relationships. So converting from polar to rectangular, I just use this formula here that we saw on the previous page. And then to go from rectangular back to polar, I use Pythagorean's theorem and also use the tan relationship between the B and the A. Now, I just showed phasors in terms of voltage signals, but in terms of current signals, it's the same thing. The amplitude of that cosine shows up here, and the angle shows up here. Notice that the frequency doesn't show up at all, and that's because it's explicit. Whenever we have a polar notation or rectangular notation in phasors, we have an implicit understanding of what that frequency is, but it doesn't show up explicitly. Here's some examples. This is my voltage signal, so the 10 shows up right here, the angle shows up right there. If I were to plot it, the imaginary versus the real part, and looking at the polar notation, I've got an angle of 45 minus 45 this way with a magnitude of 10. So when I convert that over to rectangular form, I use 10 times the cosine of theta plus 10 times the sine of theta, all times j. Now the next one is a similar signal. It's 10 at an angle of 90 degrees. So let's plot that. So 90 degrees, this being 0 degrees right there, and this being 90, is going to look like that. And in terms of rectangular coordinates, it's the same as saying that's the imaginary axis and that's the real axis. So it's a purely imaginary number. If I look now at a current signal, notice that I have no angle here. So that means an angle of 0. So if I plot it, it's going to be straight out this way. So it is exactly along the real axis and with a magnitude of 10, so it's going to have a value of 10 there. Now notice, again, that I have different frequencies here, and the frequencies don't show up at all in these phasors because it's implicit. When I look at this value here, I have to keep in mind that that frequency was at 500 radians per second. Now, this particular case, I've got a sine wave. In order to represent it as a phasor, I have to first convert it to a cosine, and I did it by subtracting off that 90. So this becomes 70 degrees, or minus 70 degrees. So I get 10 at minus 70, and I use my standard formulas for converting from polar to rectangular, and I get this. Now, most calculators will convert from polar to rectangular for you, so you don't have to remember those formulas. Now, I want to go back to looking at phasors of real signals. This is back to that oscilloscope trace that we had, and I'm just going to redraw it over here so you can see a little bit better. Again, the input is shown in green and the output is shown in blue. So in terms of phasor notation, the amplitude for the input signal is 1 and the angle is 0 because it's a cosine right there with no angle, no lag to it. So that's this one. Now the output, the amplitude is 0.7. And we already looked at this, and let me remind you, we already looked at this, that theta was equal to minus 45. So that's what this signal looks like in phasor notation. I'm going to look at a few other cases that we might see. This is a particular case where we've got the input and then the output. Now let's look at this. Remember that this is one cycle, and that's 360 degrees. The delay here is half that. So the delay in the output signal is half that. So it's at 180 degrees. And because it's to the right, it's minus 180. And the amplitude is the same as what we had up here, so it's 0.7. So this is 0.7 and 180 degrees. Now this one, the delay, let's see, this is 360, this is 180, this is half that, or 90. So the delay is 90, so I put a minus in there because it's a delay. It lags to the right, and again, the amplitude is 0.7. So in this particular case, if this is 180, that's 90, this is right there. That is half of 90, or 45. Again, because it's to the right, I make it a minus 45.7. So this is the exact same signal that we're seeing right there. Let me go through a couple of more slides really quickly with working with phasors. If I have to add or subtract phasors, I have to use rectangular form. I'm just showing an example here. If this is my first frequency, my first voltage, and this is my second voltage, I have to have the same frequency here in order to add these together. So I want to add these together. Trigonometrically, it would be really hard to do this. It's just messy. But in phasor form, it's a little bit easier. I convert this to phasors, 7 at 30, 3 at minus 60, and then I have to convert them over to rectangular form. And then from rectangular form, I just add these together. So I add the real parts and I add the imaginary parts to get this. Now, this is a phasor in rectangular form. That's the sum of those two. And then I can go back to polar notation right there. So again, I have to use rectangular form if I want to add or subtract phasors. If I want to multiply phasors, it turns out it's easier to use polar form. I don't have to, but it's easier. So for example, if I want to multiply these two phasors together, I multiply their amplitudes, or their magnitudes here, and I add their angles. So if I divide two phasors, I divide their magnitudes and subtract their angles. As an example, let's look at this is V is equal to 5 at 30, I is equal to 2 at minus 60. If I want to multiply them, that's 5 times 2 is 10, and that's 30 plus a minus 60 is minus 30. If I divide them, then it's 5 divided by 2, and then 30 minus a minus 60 is 90 degrees. To summarize the key concepts that we've gone through in this lesson, we've introduced the idea of phasors, and the phasors are going to help us to solve circuit problems. Now, by convention, we represent our sinusoids in this form with a cosine and an angle to it. We introduced phasors in both polar notation as well as rectangular notation. We also tried to relate the phasor notation, like right here, to what real signals will look like. Then we showed how to work with phasors. By adding and subtracting, we said that you have to do it in rectangular form. And multiplying and dividing, it turns out it's easier to do in polar form. And just as a reminder, whenever we're working with phasors, we're trying to combine them by adding and subtracting or multiplying and dividing, we have to make sure that we use the same frequency. We can't combine phasors that come from different frequencies. All right, thank you very much.